5.3, we're going to learn something called an explicit formula for arithmetic sequences. So when you go to Google Classroom today, it's going to tell you to click on this link. It's going to take you to Google Classroom to this investigation. So we're just going to kind of work through the slides together. Complete the warm-up. The recursive formula for the following sequence, -4, -2, 0, 2, 4, 6, 8, is shown to the right. To write a recursive formula, you need to write two things. The starting value, so here it says a sub 1 equals -4, there's the starting value, and the rule relating a term with the previous term. So here, for any term a sub n, you take the term before it, a sub n minus 1, and we're going to add 2. Is the sequence above arithmetic or geometric? How do you know? So you're going to go ahead and fill in your answer here. If you take a look, you're looking for, is there a common difference or a common ratio? Are we adding the same thing every time to get to the next term, or are we multiplying? And if we're adding, it's arithmetic, and if we're multiplying, it's geometric. So if you take a look, we see that here we're adding 2 every time, and so that would make the sequence arithmetic. Can you write the recursive rule for this sequence? 10, 12.5, 15, 17.5, and then it keeps going. So again, remember there's two things that you need to write the recursive formula. First, we need the first term. We want to say a sub 1. So in order to get a subscript, we're going to hit shift and then the underscore button. So I'm going to hit a, shift, the underscore 1. So there's the first term, equals, and our first term here is 10. So in a recursion, you have to tell someone where to start and then what to do after you start at that number. So here we're starting at 10. And then our rule here is we have a common difference. Again, this is arithmetic. We're adding the same number every time. To figure out what we're adding, all we have to do is take one number and subtract the number before it, and we'll get the common difference. So I would subtract 12.5 minus 10, and I get a common difference of 2.5. So our rule is, for any number, so I'll do a and then an underscore n. All right, so for any term, we take the term before it, and we're adding 2.5 to that. So you would type in your recursion and you would submit that. Let's talk about stadium seating. A stadium with 75 rows has 10 seats in the first row, 15 seats in the second row, 20 seats in the third row, and so on. Let's write the recursive rule for the situation. So we have to tell someone how many seats there are in the first row so that we can keep doing the pattern to find each row after that. So here our first row, it says there's 10 seats. So we'll say a sub 1 equals 10. Start with that. And notice the seats are increasing by 5 every time. So again, another arithmetic sequence. So we'll say for any row, a sub n, to find the number of seats in the row, you would take the row before it, so a sub n minus 1, and we're going to add 5 seats to the previous row to find the next row. And then you would submit your answer. Same problem continued. If I were to ask you to find a sub 6 in this situation, what am I asking you to find? And you're asking someone to find how many seats are in the 6th row. And then I'll ask you, find a sub 6. So there's a few ways to find a sub 6. One way is we could make a list. So we know that in the first row there's 10 seats. In the second row there's 5 more, so 15. In the third row there's 20. So then I would just keep adding 5. So all I'm doing is adding 5 to the term before it. And we can see that in the 6th row there's 35 seats. So again, we know that we're adding 5 every time. We could make an organized list. There's one way to solve. So again, what am I asking you to find? How many seats there are in row 6. And then I found a sub 6 to be 35 seats. All right, so you would submit your answer. It says complete the table below. X is the row number, which is the independent variable, and Y is the number of seats in that row, the dependent variable. And again, we know we're adding 5 every time, so this is kind of the work that I did on my iPad here. All right, so take a look at what that looks like. When we graphed the stadium seats data, what did it appear? Was it linear, quadratic, or exponential? And you can see this makes a straight line, so we're looking at linear data here. If data is linear, we can model it by using the equation y equals mx plus b. What does the m stand for? And m is next to the x, m is the slope. What does the b stand for? And that stands for the y-intercept. So we could use y equals mx plus b to write this thing called the explicit formula, which means like in the explicit formula, if I give you the row number, you should be able to plug it in and tell me how many seats are in that row. It doesn't depend on the row before it. So this is in the sequence of number of chairs per row, 10, 15, 20, the first term is 10. In order to use y equals mx plus b, you would need to go backwards or shift it back to find the y-intercept one term. So we need the zero term essentially to find the y-intercept. We can get this by shifting the equation back one term to get the zero term or the y-intercept. And so that's where this equation comes from. We have our starting value a sub 1 plus what is going up every time, but this n minus 1 is going to shift it back, so we are actually starting at the y-intercept with the zero term. So this is the explicit equation to find how many seats would be in any row number. So here I don't have to know, in the explicit formula, you don't have to know the previous term to find the next term. Here you just need to know which row you're looking for, and then you can plug it right in as n, and that would give us how many seats are in that row. So here n stands for the term number, a sub 1 again is the first term, and d is the common difference. So let's practice finding the right formula. Let's plug in and see what matches here. So again, when I'm plugging in, and again I'll show it on my iPad, give me 1 minute here. Okay, so I'm going to drop this down. Let's plug in. And what are we plugging in for? It's just saying, what's the right formula? Okay, so let's plug in. In this problem, a sub 1 is the number of seats in row 1. So I would put in a 10 for a sub 1, and d is the common difference, which is what is it going up by every time? It's going up by 5 seats every row, and then we'll keep the rest the same. So here is one way to write this equation right here. So let's see if that is an option. Okay, so again we have 10, and we're adding 5 every time. And the reason why I chose this one is, well, our starting value is 10, and we're adding 5 every row. From the previous slide, we know, okay, so that was the correct formula. Muna says the correct equation can also be written as this. Is she correct? Why or why not? And let's take a look at simplifying this. So for simplifying, I can distribute the 5 here, and I have 10 plus 5n minus 5, and we'll combine like terms here. 10 minus 5 is 5. So take a look. Muna is correct because if she were to simplify that and combine like terms, we get 5 plus 5n. And this is more in the format of y equals mx plus b. We can see that our slope is 5 right here. It's next to the n. It's going at 5 chairs per row. And here the y-intercept, the starting value is 5. And so this is saying if there was a row 0, how many seats would be in it? And we started with 10 seats in row 1, 15 in row 2, and 20 in row 3. So let me write that. It was 10, 15, 20 in row 1, row 2, row 3. So it makes sense that if there was a starting value, if there was a row 0, that there would be 5 seats in it. So this actually is the same equation as the explicit formula. It's just simplified. So Muna is correct. Why do we need the explicit formula? A stadium with 75 rows has 10, okay, so this is the same problem. What if I asked you to find a sub 30? So that's saying how many seats are there in row 30? Instead of making a list and adding 5 every time, it's probably going to be faster to use the explicit formula. So we can use that to calculate a sub 30 by just plugging in a 30 for n. So again, to find a sub 30, instead of just keep continuing our list until we get to a sub 30, it's going to be a lot faster to plug in to this formula right here. All right, so n is the row number, and again, we want how many seats are in the 30th row. So we would say a sub 30 in the 30th row. 10 plus 5, and then 30 minus 1. All right, we should be able to plug this in, and I call this plug and chug because you have just all the numbers on that one side. So if we type that in, so we'll do 30 minus 1 first is 29 times 5 plus 10, and we can see that in the 30th row, there's going to be 155 seats. So we would say A, and then remember shift underscore to get the 30, and then an arrow over, equals, we got 155 seats, and you would submit that. All right, so let's practice. The rest of the lesson is practice with the explicit formula. An amusement park season pass costs $26 for the first month and $10 for each additional month. Stacy thought this was a good deal and decided to pay for it. Which of the representations below model how much Stacy will be paying? Select all that apply. All right, so our starting month is $26, so it could be the first one. And we're adding 10. All right, so we know it's going to be the first one, not the second one. That's subtracting 10. And then we could simplify. Okay, so let me show my work for simplifying. Okay, so we have A sub n equals $26. We're adding 10 every month. Let's simplify this and see what we get. So you would distribute. We would get 26 plus 10n minus 10. We'll combine like terms. So this is like going backwards. Instead of month 1, we would go to like month 0 if there was a month 0. It's 16 plus 10n. So here's another way to write this. Or if we're writing y equals mx plus b, it would be 10x plus 16. So that's several different ways to write it. Let's see if there's anything that matches. Okay, so we started with 16 plus 10n. Okay, so this one would match. This one would also match. So there's a bunch of here that are actually equivalent, and using these we would all have actually the same, we would get the same answer. Darby has agreed to donate $196 to Knoxville for its library. In addition, she will donate $3 for every book a student or child that visits the library reads during the month. The sequence showing the possible outcomes for Darby, she could donate $196, or if a child visits and reads, then it would be $199. For the next child, it would be $202, $205, $208, and so on. Which representations model the situation? So we know we start with $196. We're adding 3 every time, so again, it's this first one. If we simplify it, let's take a look at what that would be. And again, I'll show my work here. So we have A sub n equals, we start with 196. We're adding $3 per child. We can distribute and combine like terms. So we have 196 plus 3n minus 3. We'll combine. So 193 plus 3n. Here's another way to write this. And let's see if that was something that was listed. So here's the 193 plus 3x. That will also work. And 193 plus 3n. So again, 3 representations that work for that one. I should go back so let you look at that. Okay, next. Emerson is a stingy donor. She donated $168 to Reeves Rogers for its library, but she can't stand a certain book series. Every time she sees a child reading a book from that series, she's going to take back $8. So here is a sequence of numbers that represents her taking back the money every time she sees a child reading that certain book. All right, so again, which representation to model this? So we start with 168, and we're subtracting 8 every time. So here's the first one in the explicit formula. We can distribute and combine like terms. All right, so I'm going to write that down and distribute. So we have A sub n equals 168 minus 8 times n minus 1. Okay, so let's distribute. So we have 168 minus 8n plus 8. We'll add, and we'll get 176 minus 8n. All right, so I'm looking for a y-intercept of 176, but we're going down 8 every time. So this one would work, and this one would also work. Oh, sorry, didn't give you a lot of time. Okay, so those are 3 that mean the same thing. Match the following tables with the explicit formulas that they represent. Not all choices would be used. All right, so I'm just going to pick one of these tables here. This starts at $84, and it's increasing every time. Looks like it's increasing $16 every time. How I know that? I'm just going to take one number and subtract the number before it. Every time I do that, I get 16. So I'm looking for, is there one that starts at 84, and we're adding 16 every time? And these would match. Okay. Let's try this one. This is 60 and it's going up by 20 every time. Okay, so that would match that one. And this one right here is 125, but it's going down 25 every time. Okay, so I've matched all these up, and let's just see if any of these other ones would, nope, that's it. Oh, I have 6 out of 9. Is there more that match? Oh, but these ones don't match. 125 minus, yeah, okay. All right, so now we've completed the lesson, so you're going to head to Delta Math and complete 5.3, the explicit formula for arithmetic sequences. You can close out of this tab. Everything's been recorded, and I'll give you points for working on this.